Okay, so we're going to try to wrap up chapter 17 pretty quickly here and then move on to chapter 18, which is on the beginning of our journey through optics, which I guess will be a very rapid and yeah, probably tricky journey, but hopefully we can get it done before the end of the summer session too. But just going back to where we were yesterday, I think a few people came up to me afterwards and posed some good questions. So I wanted to just take the time to explain, to come back to this slide. So when we're looking at this that long equation, but let's just focus on the part we really need here. So when we're looking at this phase difference equation for two waves, so what's happening here is that we have the same signal, the same frequency, the same amplitude, everything about the two waves are the same. And these can be sound waves, these can be light waves, these can be ocean waves. As we've seen, the type of wave at the level that we're analyzing things in this class really doesn't have much of an impact on the formula. But what's happening is that these two identical waves are being emitted by two separate speakers. And there are two ways that we can have these waves in relation to one another. So where the crests and troughs are in relation to one another, that we can have that shift. So these phase changes are just shifts in terms of angle space, which is like the argument that's going into the sines or cosines. So one way that we could have that shift is by just having the waves start off when they're leaving the speaker being out of sync. So the moment they leave the speaker, not even thinking about where the speakers are in relation to each other, but just, for the case of sound, the sound wave as it's emitted from speaker one versus speaker two, that could be at some different point in the wave cycle. So that's this delta phi naught. So this is at the level of the speaker, maybe is a way of thinking of it for sound waves. And then this 2 pi delta x over lambda, this is due to the fact that the waves have to catch up with one another. So this is due to the position of the two speakers in relation to one another. So we can see in this picture a few possibilities. So on the left, the speakers are at the same location. So there's no delta x. Delta x is 0. Just write that. I guess it's already written here for us. But when one wave is playing a peak, the other wave is playing a trough. So you can see here when this wave is at a peak, this wave is at a trough. And so as a result, these two waves have an initial phase difference, a delta phi naught of pi radians. They're completely out of phase, we would say. So they destructively interfere, and these two waves in the region that we're looking at here would just completely cancel one another out. Now, in the middle picture, the two speakers are playing exactly the same sound at exactly the same place in the cycle. So we say that the initial phase difference is 0. When one wave is playing a peak initially, the other is playing a peak initially. But you can see that the waves don't constructively interfere, which is what we would expect if we have two speakers being synchronized. And so why do they not constructively interfere? Well, because the speakers aren't located at the same place. So in order to think about, do these waves overlap or not, we have to look at one location, where are the waves in relation to another in their cycle. And so you can see, even though the waves, when they've left the speaker, they're synchronized, because of this delta x, which is in this case 1/2 of a wavelength, what happens is the speaker 2 has to travel half a wavelength farther before it gets to that same position as the waves from speaker 1. And by traveling half a wavelength farther, that wave is now out of phase. So they were synchronized, but speaker 2's sound had to travel half a wavelength farther, which means that where there once was a trough, now there's a crest, or vice versa. And so now, again, we see destructive interference in this image B, and this is purely due to the fact that these speakers are not at the same location. And then in picture C, we have the mixed case, so the general situation where here there is some initial phase difference. So when this speaker is emitting a peak, this one is emitting at zero, like an increasing zero. But there's also a separation between the speakers. And so this is where we really have to rely on our equation, because it's hard to see what would happen, intuitively versus the other two situations. So here we say that delta phi equals delta phi naught, which in this case is pi over 2, plus that 2 pi delta x over lambda. And in this case, delta x is lambda over 4. So we can just plug that in. The lambdas cancel, which is the benefit of talking about the delta x in terms of a wavelength. It lets us just cancel that lambda. And then 2 pi over 4, this is another pi over 2. So when we add these two things up, we get a total phase difference of pi, which tells us that this image C, is also completely out of phase. We say out of phase for a phase shift of pi, just to help clarify that language. And so we again get destructive interference, where there's a peak on the other, on one, there's a trough on the other. So they just cancel out. So all three of these images end up with the same observed phenomena, which is there's no sound in that region, in this line at least. Now, if we go off the line, there will be sound, and it will be tricky to see where it interferes, but that's what we're going to see in a couple slides. But at least on the line, which is what this equation is designed to help us with, these two speakers can produce the same interference pattern, whether by initial phase difference, spatial difference, or a combination of the two. Okay. So then in the example we did, all of these example cases actually take delta phi naught to be 0. So I know I wrote yesterday and kind of briefly mentioned, well, we could also get the same behavior that we observe here with a delta phi naught. I just wanted to allow you guys to see that, which is also something you can see in this slide with pictures A, B, and C. But to answer this problem, the way they frame it, all that you need to do is say, okay, how does my delta x change based on each of these shifts in position? And then plug into the formula. So the only formula you need for this one, since delta phi naught is 0, is just delta phi is 2 pi delta x over lambda. And then you just plug in all of the different delta x's as they, So for example, when they say move forward 1 meter, but speaker 1 was initially 1 meter, so behind speaker 2. So this one makes delta x 0. Whereas this one makes delta x equal to 2 meters, because we start off with this 1 meter separation. So all of these just create some delta x, we plug them into our equation, we get a delta phi, which is the phase difference, and then we can ask, is this delta phi, oftentimes for these sorts of problems, it'll either be like 0 or pi over 2 or something like that. And so we can say, well, if it's pi, that's destructive interference. They're out of phase. When one is high, the other's low. And if it's 0, then they're in phase. When one is high, the other's high. And if it's something in between, then it's a little trickier, but that's actually what we're going to talk about next. So if it's something in between, for any arbitrary phase difference, we can get the amplitude, so the biggest possible combination of the two, with this pretty nice formula. So the examples we've seen so far are if delta phi is 0, we call this the constructive interference case. So if delta phi is 0, what happens to this formula? Well, we have A equals 2 times little a times cosine of 0, but this is just 1. So we can see that is in fact constructive interference. The amplitude of our resulting wave is twice the amplitude of our individual input waves. And then we've also seen the destructive case, where delta phi equals pi. And so in that case, we have A is 2 times little a times cosine of pi over 2, but we know cosine of pi over 2 is 0. So this is 0, and those waves would completely cancel one another out. But you can see in these pictures here on the right what happens for different phi's. So if it's not purely destructive, not purely constructive, we get some combination, and all you have to do is plug into this formula, and you'll be able to find what the amplitude of the resulting wave is. So in all of these pictures, the red and the green are the two things you're adding together, the two waves that are interfering, and the blue is the result. It's what you would actually hear if this was sound. It's what you would see if this were light. And so you can see, for example, in this top picture, that the waves are almost perfectly constructively interfering. So we have a delta phi of 40 degrees, which is close to 0. And so the resulting amplitude we get for this blue curve is almost 2 times little a, right? It's not quite perfectly constructive, but it's definitely overall, the effect is that it's more constructive than destructive, you could say. And so this is a type of question they might ask you, which is like, for some situation, and then you'll use that situation to calculate a phase difference. So maybe they'll tell you an initial phase difference and a difference in the position of two speakers, or they could do the same thing with lasers, or with ocean wave sources. And so they could say, for some phase difference that you may have to calculate or may be given to you, is this constructive overall, or is this destructive overall? And to answer that question, if it's not a simple case of the phase difference being 0 or pi, what you have to do is you have to look at these amplitudes. So any amplitude greater than little a, we would call this, somewhat constructive. I'll put somewhat, so it's not confusing with the case where delta phi is 0. And any time where this amplitude is less than little a, we can call this, somewhat destructive. And so if you're given a problem where they're asking you to determine for some arbitrary phase, is this, more constructive or is this more destructive? This is kind of the condition you'll be interested in. And you can see it's just from plugging into the formula, basically. Once you get a phase difference between the two interfering waves, you can very quickly get the amplitude of the resultant wave that you find from adding them up, which is the principle of superposition. Okay, so are there any questions on this? This is, so far, all we've been doing is superposition along a line, so one-dimensional. We're about to make the jump to 2 dimensions, so it's good to ask any questions you have about this material now, so that we can move on to the harder stuff. Okay, so I liked this picture. I don't know who made it, but it was just a random Google search away. But we've probably all seen, I don't know about the case of synchronous people fishing, but if you look at a pool or a puddle on a rainy day and you see raindrops falling onto the surface, you'll notice that if there's just one raindrop that falls, that you get these circular waves, which was a topic we discussed in chapter 16. The fact that if you have a 2-dimensional boundary, like the surface of water, then you get waves that travel outward in circles. And that if you look at those waves far enough away, they look like they're just plane waves that are linearly spaced, even though technically they're part of some big circular arc. But what we're looking at here in chapter 17 is, okay, what happens if you have 2 raindrops? I know we're taking baby steps in some ways, but it's a really beautiful phenomenon. I remember just being obsessed with this at some point in undergrad and like spending way too long looking at rainy puddles. But you can see that in some locations, like here, for example, and here, that the 2 crests of the waves overlap. And so we get constructive interference. We get a larger amplitude at those points. Whereas at other points, these dark spots, we get the opposite effect. We have troughs overlapping. And so we get, so here we have troughs overlapping. So we get constructive interference, but sort of the other way around. And then when we have a peak and a trough overlapping, which is happening here, for example, or here, then we get destructive interference. So in those situations where we have a peak and a trough, the waves cancel out and we get zero amplitude. So we can have, all types of interference because this is two-dimensional now. So in 1D, we find the phase difference and we say, okay, well, the two waves have this phase difference. So everywhere along the line, they're either going to be helping one another or hurting one another, vice versa. But in 2 dimensions, we have, an infinite number of lines. And so on some of those lines, the waves will be helping each other. And on other lines, the waves will be, subtracting from one another. And so we have some nice conditions here. You'll notice that before you get too busy writing these formulas, that it's really the same formula that we were just looking at. The only difference on this page is that instead of delta X, we've written delta R. And so the idea here is that we can use the Pythagorean theorem, which you may have already been doing on your homework, to find something akin to a spatial separation. So even if the speakers, for example, aren't on the same line as the point where we're trying to think about the interference, we can just look at how far is it from speaker 1 to the point we're interested in, how far is it from speaker 2 to the point we're interested in, and the difference in those two links. So subtracting R1 from R2, we get delta R. So it's very, very similar to how we get delta X. And so just to give you a pictorial representation of this, you can see on the right here, we have 2 sources of waves. So this little blue, star-like thing is one wave source, and this little green one is another wave source. So those are our wave sources. And then positions A, B, and C are places that we're interested in analyzing. At this location, what does the interference look like? Is this going to be somewhere the waves are helping one another? Is this going to be somewhere the waves are canceling each other out? So we're trying to figure out what's happening in that respect. So for example, when we look at position A, you can see that R1, the position from, let's call this one 1 and this one 2, maybe. So the position from source 1 to A is 2 lambda. And the position from wave source 2 to A, we could call this R2, is 3 lambda. And so delta R, we can always just take the magnitude of delta R. It doesn't really matter if one is longer than another. Delta R is simply lambda. Okay, and so since delta R, so we can see that this condition, if we don't have any initial phase difference, then in order for us to have constructive interference, for example, we have 2 pi delta R over lambda. Has to equal m times 2 pi. So you can see we can cancel the 2 pi's. And we can say that for constructive interference, delta R has to be some integer times lambda. So if the difference in the travel path between the 2 sources of waves, if one had to travel an integer number of wavelengths farther, then that causes them to line back up, right? It's kind of like one spent a little longer, but because these things come back together after one wavelength, so because the wave repeats after one wavelength, we end up at the same place that we left off. So, they're overlapping from the source, but one travels 1 extra wavelength and now they're overlapping again. And so that's what these conditions are here on the left. We have another one for destructive. We just stick a 1/2 in there because it's going to happen in between the constructive places. And so at point A, we get constructive interference. We have a multiple of lambda for our difference in position. And you can see, in fact, at point A, that one of these wave fronts from the green side lines up with one from the blue side. So we have this one lining up with this one, so that indeed is constructive interference. However, you can see at position B that we have a different case. So our R1 for position B is 2.5 lambda. Our R2 is 3 lambda. So our delta R is 1/2 lambda. And so you can see that in this case, we have a 1/2 multiple of lambda. So that's the case where we get like complete destructive interference. So at position B, the water will be just at the same height as it would be if there were no waves around. And so we can see that in this picture by the fact that there's a crest of the green wave while simultaneously there's a trough of the blue wave. So those two will cancel. So when we draw these images, the lines, the circles, tend to be placed on top of the peaks. And so directly in between those lines will be the troughs of the wave. So this is like a peak of the wave, whereas this point is like the trough of a wave. And so then somewhere in between these two will be where the wave passes through 0, right? Where it's doing something like this. Okay. And so we can actually draw some lines, and this is where it starts to look a little scary, but we can draw some lines where the waves will always constructively interfere and where the waves will always destructively interfere. And so this is, we end up getting hyperbolas, so a conic section you may have seen. And so for example, let me see how we can talk about this most easily. This delta R equals lambda here. So for all of the points on this red line, the distance from the green source, sorry, let me choose, you're just using all the colors here. Maybe I'll use orange. So the distance from this green source to anywhere on this red line will always be 1 length lambda farther than the distance from this blue source to anywhere on this line. And so as we go outward farther and farther, both of these R1 and R2 get larger, but the difference, delta R, stays at delta lambda. So every point along this red, now orange line will have maximal constructive interference. Whereas on the black lines drawn here, every point will have maximal destructive interference. So those points will be at surface level in height. They won't have any displacement. Okay. And so just like in the case of standing waves, we can call the red lines here antinodes because those are where we get constructive interference. And we can call the black lines nodes. That's where you get destructive interference. So you won't have to actually find these lines like on your own in this class. It's just good to kind of see the structure, I think, so that you have an idea of what's going to happen when you're solving these 2D problems. But you will need to use these two formulas basically, or in general, these phase difference formulas to find the phase difference at some point of interest based on the delta R from 2 separate sources in 2 dimensions. And you can do the same thing in 3D. The formula is exactly the same, but instead of using the 2D Pythagorean theorem, you have to use the 3D Pythagorean theorem, which really isn't much harder. So it's just x squared plus y squared plus z squared equals r squared. So it looks almost identical if you haven't seen it before. I don't anticipate asking you to do interference in 3D in this class, just because it takes some practice and it's just a lot of messy geometry. But I believe there are at least a few 2D interference problems on the homework, so you will get some practice with those. And in effect, we're using the same type of apparatus as the linear interference in 17.6, but just with this delta R. So you'll have to throw in some Pythagorean theorem stuff. Now, from office hours yesterday, I know one of these problems is really annoying. So if you run into the one that's just really hard to solve algebraically speaking, like once you set it up for delta R, there's one that's really hard to solve algebraically, just use Wolfram Alpha. So it's a really helpful tool. If you just search wolframalpha.com, and you can type in the equations with the variables and it'll solve them for you using a computer algebra system. So don't abuse Wolfram Alpha. It's good to learn how to do this yourself so that you can solve problems quickly and efficiently, and also solve them in the final, I guess. But if you run into some 2D interference problems, especially that just have lots of square roots and squares and things are super terrible, just plug it into Wolfram Alpha and don't worry about it too much. Okay, are there any questions on the 2D interference before we move on? Okay. So the last section in chapter 17 is on the topic of beats. And beats are a really weird result of, again, trig identities. So like almost everything we learned about in chapter 17 just comes down to trying to add up some waves and then using trig identities and finding something kind of weird or surprising. And so the idea with beats is that if you play two sound waves, so now we're not talking about interference in the way that we have been. So in all the other sections in chapter 17, we've always been considering two identical waves, so the same frequency, the same wavelength, that are just offset in phase. So that could be a result of the speakers being at different positions, and so the waves reach you after having traveled different lengths. Or it could be that the speakers themselves are just emitting waves that are the same wave, but just at different positions in their cycle. But for beats, you actually do need to have waves with slightly different frequencies. So we're going to have F1 and F2, so two different frequencies. And in general, for beats to occur and for them to be measurable, the frequencies do have to be pretty similar. So usually, if you have like 100 hertz frequency, maybe you could have up to like 110 hertz or down to 90 hertz as the second one. And that would be the sort of range of values where you would expect to actually be able to observe beats occurring. And the idea with beats is that if you have different frequencies, so the red and green sinusoids here are different frequency waves, at some places they will constructively interfere, but because they're different frequencies, they're going to slowly come out of phase just due to the fact that one wave takes longer to make a cycle, basically. Right? They have different frequencies, so they don't just cycle at the same rate. One wave will be cycling very slowly and the other will cycle a little bit faster. And so sometimes they'll roughly line up and sometimes they'll roughly cancel out. Okay. So I know it's hard to imagine maybe, but walking through this picture either right now or if you want to come back to this, I think can be really helpful. So you see this blue curve is just the superposition of the red and the green. And so in this region where they overlap exactly, we get constructive interference. But then because one of these is slightly longer than the other, since they have different frequencies, eventually they'll come completely out of phase. So here the phase difference is pi. And so the resultant wave is just not a wave, it's just destructively interfering. So there's a node there. And then we keep on going, and again, they'll come back into phase, and we'll hear another constructive chunk of the wave. And so the thing that we actually observe when this happens is we observe the constructive interference occurring at some point. We observe the destructive interference happening at some other point. And so you can see that there's some envelope we can draw, which is this red dashed line that's going to be itself a sinusoid, but just with a much longer wavelength, okay, a much lower frequency. So you can see in this picture, we could draw it here. We start here, and it looks like this. So this is only half of a wavelength. So this whole length here is just lambda over 2, even though the waves themselves have had like 10 wavelengths over the course of this picture. And so when you have beats occurring, what happens is, you can play, and this is a tool sometimes used in tuning musical instruments. So you can play a note like on a piano, you press a piano key, and then you could have a speaker play the sound you want that piano key to produce. And what you'll hear is that if the two sounds are exactly the same, then you'll get a consistent type of interference. So the sound that you hear will be a constant volume. Now, if depending on the phase, right, on the locations and the initial phase, those two sounds might constructively or destructively interfere when they hit your ear. But if you stand still and play exactly the same two tones, then you'll just hear sound at a constant volume. However, if you play the sound you want your piano to play and you press the key and it's different by a little bit, then you'll have a situation like the case here where you have an F1 and an F2 that are slightly offset. And so as a result, you'll hear this as a very or a comparatively low note. Typically, these can be even below the human range of hearing for very close things, right? Humans can only hear down to about 20 hertz. So you have to have a beat frequency of 20 hertz or greater to make it audible. But you can create these such that you can actually hear them. And it sounds like this very low note, which is often strange because it's coming from a combination of two high-pitched notes generally. And it turns out that after doing a ton of trig that I'm not going to reproduce, but that is shown in the book if you're interested, we get the world's simplest formula, which is that the beat frequency is just the difference in the two frequencies that you're playing. So these problems are often just really, really easy. I'm not even planning on really giving you too many of them because they're maybe too easy. So for example, if we have 105 hertz here and we have, I don't know, 92 hertz here, then the beat frequency is just the absolute value of the difference between the two. So here that would be 13 hertz if I can subtract. And so that would just be for this red dashed curve, the frequency of that wave. So the thing to keep in mind is that you can get the same beat frequency in this case, or if we had an F2 of 118 hertz. So if we had these two waves playing, we would get the same beat frequency. So there are always multiple combinations that can achieve the same frequency. And so the only way that you can write an even sort of hard problem about beats, in my opinion, is to ask someone like, okay, what are the possible frequencies? And then what are the wavelengths of those possible frequency? You can kind of ask some basic traveling wave questions like that. But in general, the beat frequency itself should be always very easy to find or to work with. Okay, and so that's the end of chapter 17. So before I move on to chapter 18, which is similar, we're still talking about waves, but it'll be, some new features, new phenomena. Are there any questions or anything people want to go back to while we're here? Okay, so chapter 18 is on the topic of wave optics. And so the first thing that we have to do is actually talk about what we mean by wave optics, and then compare that to what we're going to learn in chapter 19, which is what you may have already learned in high school a little bit of, which is ray optics. So this is just a fun picture I found, but it's not too important for this class. But light in general, we can think of in different ways. And that's a result of basically the fundamental nature of light being a rather tricky quantum mechanical phenomenon that we can make a lot of approximations with, but that at the end of the day, as any physicist will tell you, light is simultaneously a particle and a wave. And so it simultaneously has properties that we associate with particles, like the fact that we can talk about light in terms of little chunks, which we often do in the context of atoms, right? If we have electrons hopping between orbitals, we think of light being emitted in little chunks. But in other situations that we'll see many examples of in chapter 18, light is better thought of as a wave. And the way that occurs generally is that for sort of quantum systems, so things like atoms and molecules, the particle nature of light becomes very critical. But for systems that are larger scale, but still small enough that they're at basically the wavelength of light, the wave nature becomes very critical. And then for even bigger scales, so things like human scales and rooms and stuff, or glasses, lenses, we can treat light as a ray, which is just to say that we can imagine the light travels in straight lines and doesn't really do anything too exciting. And so that will be the topic of chapter 19. So I don't expect you to read all this stuff, but I just think this is a decent picture to kind of show everything simultaneously. So the wave model is what we're about to talk about on the left. And this is where we can use the ideas of interference and traveling waves, so what we've been learning about so far, and we can just apply them to the context of light in some weird systems. The ray model, which is what we'll talk about soon, this is what you'll use in the context of like lenses and mirrors, so sort of larger scale optical devices. And then the particle model of light, we don't really get to talk much about in this class, unfortunately, but it is part of the topic of 3C, and you'll also encounter it oftentimes in chemistry when you're trying to think about atomic spectra, that sort of thing. And so to show you an example, so on the left is, I think, a good example of the wave nature of light, whereas on the right is an example of the ray nature of light. And you can see that the only difference between these two pictures is that on the left, the size of that opening is similar to the wavelength of light. And so a really, really helpful idea in optics is that if you're dealing with some optical instrument that has some scale L, so you can see in this problem that L is like the size of the opening. So this opening is like what we would call L. But in a different problem, L might be some different sized thing based on what type of system we're interested in. So if L is about the size of the wavelength of a wave, then we should expect that thing to have to behave really similarly to a wave. If L is much, much smaller than the wavelength, that's where we have to start thinking about particles. So that's why at the quantum scale, like at the level of atoms and molecules, particles become really important. And whenever L is greater than the wavelength, or much greater, then we have to start thinking about the ray nature of light, which is what we tend to have the most intuition with. So our everyday life is characterized by thinking of light as a ray. So for example, when you open a door in your house at night and there's a light on in one room and it's dark in the other, we kind of see the light coming through that door and making a crisp shadow, that just traces out the outline of the door. So that's an example of light acting as a ray. So by a ray, I just mean that the light is traveling in straight lines. It's not doing any funky wave interference stuff. It just, goes through the opening of the door, hits the ground, makes that little, rectangular shadow shape, and that's the end of the story. But you can see that when we have a small enough opening, that the light will actually expand a bit as it travels through the opening. And so that's a wave property. So when waves travel through openings that are similar in size to their wavelength, they will actually expand, which is often called diffraction. And so diffraction is something that we actually can see, at least in the context of ocean waves. So if you ever put two rocks together in the ocean water and see waves pass through it, once they get through the rocks, they'll tend to spread out on the other side, because at any human scale of rock placement, you'll be not too far away from the size of a an ocean wave's wavelength. So you tend to really see the wave-like properties of ocean waves because they're quite large waves. For very low sound frequencies, so sound, we have to be careful in thinking about diffraction, because oftentimes you might think something is diffraction when really it's just reflection, right? So if I had another wall here, then some of this would reflect off and the wave would end up in this region even without diffraction. Okay, so we have to be careful about confusing the two. But with low frequency sounds, we actually can have diffraction, even in an opening the size of a doorway or something. So this is part of the reason that low frequency sounds tend to kind of spread around, fill up a house. If you've ever had someone, outside using some lawn equipment or something, it tends to be very good at diffracting through openings. And that's a result of the way that we split light's properties up in terms of the size of the wavelength in relation to the size of the apparatus. So in this case, openings. Okay, so for the rest of the chapter, though, we'll just assume light is acting as a wave, and we'll constantly justify this to ourselves by thinking about the way that the scale we're looking at is roughly the scale of the wavelength. Okay, but for all of chapter 18, we'll be using this wave model of light because it will be appropriate for the types of phenomena that we'll be discussing. So all of them will have characteristic lengths that are similar to the wavelength of light. And chapter 18 is entirely focused on light, just like chapter 19 and 20 are pretty much. So the rest of the class is almost entirely focused on thinking through the results of the physics of light. Okay, so our first example, where we have a structure that is similar in size to the wavelengths of light, is so-called thin films. And so one example of a thin film is on the left here, which is if you have a mirror, then the way that mirrors are typically constructed is that you have a sheet of glass and you put some metal on the back of it. And so what happens is some of the light will hit the front surface of the glass and reflect, whereas the majority of the light will go through the glass, hit the metal, reflect off of that, and come back out. And the result is that we get a kind of dual reflection that you can see for the left here. So the candle on the right, this is the real candle. This is the real candle here. And then these are the sort of double reflections. And so one of those is coming from the surface of the glass, and one of them is coming from the surface of the metal in the mirror. And the thickness of the glass is usually pretty thin. And so we can think of that as approximately a thin film. And what we'll see is that depending on the thickness of that glass, some wavelengths of light will constructively interfere after that reflection, and some will destructively interfere. And so another great example of a thin film is a soap bubble. So that thin layer of soapy water, when we look at it, it'll tend to be this kind of rainbow of colors. It's hard to find a picture of this, but in this one, you can at least see some blue and pink and purple tones. But if you've ever seen, for example, like oil on the surface of water, it has this really beautiful rainbow sheen. And the way that that's occurring is through this physics of thin films, which we can look at now in the context of some actual diagrams. So like I said, in order for this, for a thin film to do something interesting, we have to have basically two reflections. So this first picture, we're not yet looking at the whole physics of the thin film. I just want to talk you through what's happening when light reflects off of a surface. Okay, so whenever we have some translucent medium, so something that light can pass through, but we change from one type of material to another type of material, so we have a boundary, there will always be some light that goes through and some light that gets bounced off. So any type of boundary, so air and the glass of my glasses, or I guess it's polycarbonate plastic or something, that's a boundary. And so some of the light that hits my glasses will come through to my eyes, but some of it, a small fraction in this case, will bounce off. And then that happens on the front surface of my glasses, but it also happens to the light on the back surface of my glasses. So you can see everywhere there's a boundary between two translucent materials, so materials that light can pass through. Some of the light will go through and some will get bounced off. So that's the first idea. And then the second idea is that, very similar to the case of strings, we have two types of boundary conditions. So hopefully from chapter 17, you remember that if we have a heavy string connected to a light string at some point, then when the wave of the heavy string comes through, it easily moves the light string. And so we'll call this a free boundary condition. And in that case, if a pulse comes in, the pulse that's reflected back will be on the same side as the pulse that comes in. So this is just a review of the last chapter. However, if we have the opposite case, if we have a light string connected to a heavy string, and here I mean that in terms of mass density, just to be clear, like the weight or the mass per unit length, so the mu. So in this case, if we have a pulse come in, when it's reflected, it'll be inverted. And this is a result of the fact that the heavier string doesn't move as much. So the oscillators pulling on one another, as they come into this boundary, they run into a problem at the edge. They can't just move backwards the same way that they came, because there's a downward force acting on them from the boundary. So they get inverted. So there's some really good cartoon diagrams. If you look up videos of fixed versus free boundary conditions, you can find some great examples. And so what I want you to see here is that, so we've talked about the index of refraction. We'll definitely see that phrase many more times over the next two chapters. So the index of refraction is telling you how the speed of light changes in a material. So the speed of light in a material is the speed of light in a vacuum. This is that 3 × 10⁸ meters per second divided by the index of refraction. So for air, the index of refraction is basically 1. It's like 1.003 or something. And so for air, the speed of light is basically the speed of light in a vacuum. But if we have something like water, for water, the index of refraction is like 1.33-ish. So for water, the speed of light traveling through it would be a little bit slower, right? Like 20% slower, 30% slower. So anyways, for the string, we can just look at the mass per unit length to figure out the boundary condition. For light, we have to look at the speed on either side to figure out the boundary condition. So that's what we're doing here. So you can see case 1, which is where our N1 is greater than N2. So you can see N1 is the index of the first material, so the thing the light begins traveling in. And index 2 is the index of refraction of the second material, so the one that it's going to reflect off of partially and partially transmit through. So the transmitted wave, nothing exciting happens. It just keeps going through. So the transmitted wave, kind of boring. But the reflected wave for case 1, where we start off with a higher index of refraction, so we start off with slower light and we end with less slow light. So an example of this would be if you shine a flashlight under the water of a pool. So just to draw this out, we have a pool. So if I shine my flashlight out of the water of a pool, in the pool, the index of refraction is like 1.33. Out of it, if it's air, the index of refraction is basically 1. So shining a flashlight from underwater out of a pool would be case 1. So this is case 1. And in that case, it acts like a free boundary. So in that case, the reflected wave has the same phase as the wave that is incident on the boundary. However, if we had our flashlight and we shined it down into the water, we would be going from a low index to a high index. And so that's case 2. So case 2 is going from a low index to a high index. And so in that case, it acts like a fixed boundary. And we get a reflected pulse that does have a phase shift, and it's actually a phase shift of pi. So it's equivalent to if the wave had traveled an extra half a wavelength of distance, that basically the reflected wave, where it would have had a peak before, now it has a trough. So everything's reversed basically on the reflection. So I know these are like confusing conditions in the sense that it's just a lot of information. I'll probably give you something like this on formula sheets, I would expect. Yeah, I'll just say I will if it's something I'm making. But I do encourage you to come back to the slide or go to this section 8.2 in the book and try to understand and remember the best you can what these two cases look like and what the sort of importance of them is. And so things like water and glass will tend to have a higher index of refraction than things like air. So keep that in mind when you're trying to build the intuition around a problem. But then if you're actually trying to do something precisely, you should, of course, go look up the index of refraction of the materials in a book. Notably, the textbook has a table of them, and then compare them carefully. Okay, so now we can look at what actually happens when we have a thin film. So if you're wearing glasses, you probably have this happening on your face right now. Most glasses have an anti-reflective coating that uses a thin film to destructively interfere light that's bouncing off. And so what happens in the case of a thin film is that we have so step one, we have a wave approaching. So the wave is, let's say, in the air on the left, and it's approaching this system. Now, when the wave hits the edge of the thin film, part of it will go through and part of it will reflect. So the thin film will tend to have a higher index of refraction than air, for example. So the wave that reflects in step 2, so this wave here, had a phase change of pi, or as the book likes to say, it's as if it went an extra lambda over 2 distance. Now, the wave that's transmitted through, nothing happens to it so far. It travels through the thickness of the material, and then it's going to bounce off the glass boundary, okay? And so depending on if the glass has a higher or lower index of refraction than the film, we could either have a phase shift happen here, or we could have no phase shift happen, okay? So let's say the glass has an index of refraction in G. Let's say it's bigger than this N. So in that case, we would get a phase shift of pi for the reflected wave, the second step. And so then that reflected wave from the glass goes back through the thin film. And again, some of it will reflect, some will transmit, but we only care about the part that actually leaves the thin film itself. And we end up with these two waves overlapping. And so this is a multi-step process, I know, but just to recap, so the waves that are coming out at the end, so the waves here, one of the waves just reflected off of the film. The other wave did a couple of things. It went through the film, reflected from the glass in this case, and then went through the film again and came out into the air. So you can see the sort of the history of each of those two waves. And the result will be some linear interference. So actually thin films are one of the applications of linear interference, the linear interference equation that we were already discussing, this whole delta phi equals delta phi naught plus 2 pi delta x over lambda. So this is the equation that we use to derive these results, but we can actually say something a little bit nicer, a little bit more specific when it comes to thin films. So here, confusingly, T is the thickness. I really hate this notation. I wish they would have used, I don't know, D or something like that, L, I don't know. But T is the thickness of the thin film. So like if you get your ruler out and you measure this distance, that's T. And what we can say is that there's a relationship between which wavelengths constructively and destructively interfere and the thickness T of that material. Because the wave that I called wave 2 here, so this one, had to travel extra distance. It had to travel through the film and then back through the film. So it had to travel this 2T extra distance. So that extra distance causes a phase shift. So now if the waves were lined up, this was all the same light, so we can assume that they were all lined up so that initially there was no phase difference. But because the wave that went through the film and came back had to travel farther, there now is a phase difference. And then the tricky bit is that there can also be a phase difference because of all these boundary condition shenanigans due to the fact that we have a phase shift of pi for the case N1 less than N2. And so what these formulas say, and there's this like blue text below that hopefully helps explain them. So for the case where either both of the waves have a phase shift of pi or neither of them have a phase shift of pi. So right, there are two surfaces that things are reflecting from. There's the edge, so we might get a phase shift on this edge, or we might get a phase shift on this edge. So if we get a phase shift on sort of neither or both, then we say that this first formula is constructive and the second formula is destructive. Now, if instead we get a phase shift on one of them, then in that case, it's flipped. The equation for destructive will be the first one and the equation for constructive will be the second one. So you can see the reason for that is that if you have one wave have a phase shift while the other doesn't, then that's going to flip the two so that now they're out of phase by pi radians. So, the peak would be a trough basically. And so by doing that, where you expected to have constructive interference, where you expected them to line up, if one of the waves gets an extra factor of pi, now they don't line up. And so we exactly reverse the conditions. Whenever we would have constructive interference with either no phase shifts from reflection or both surfaces phase shifting from reflection, we get constructive. So if only one of those has a phase shift, though, we get destructive. So just to give you an example, because I know this is so obtuse in a way. So let's again take air on the left. So that would be n equals 1. Let's say that this is some anti-reflective coating. Maybe it has an N of 1.7, which is pretty high. And then maybe behind this is glass. Let's say it's 1.5. Glass is actually not just one material. Like there are tons of types of glass. So depending on the type of glass, it'll have a different index of refraction. The book should give you some that they prefer you to use. I forget what they give you, but anyways. So remember, we have the two types of wave here. So the one that just reflects off the surface and comes back, let's call that wave 1. And so here it does get a phase shift. So yes, it gets that pi phase shift because it's going from a low N to a high N. So here, yes, because 1.7 is greater than 1 is the reason. Now the second light will be transmitted and then will be reflected off this surface and come back through. And so the second light here, it's going from a high to a low. So here it's the phase shift is 0, and that's because 1.5 is less than 1.7. Sorry, I know I'm writing off the edge here. Hold on one second. And so in this situation, the destructive case would be when 2t equals m lambda over n. And the constructive case for this picture here would be when 2t equals m plus 1/2 lambda over n. So you can see when we draw our picture and we compare the indices of refraction at each layer, we can figure out which formula we should use for each case. And if it's different, it'll just be flipped, basically. Now, just to make sure you understand, the n here that we would use in these two formula is 1.7. So the n in these two formula is the index of refraction of the thin film. So the thing we care about the most is the thin film. So the T is the thickness of that film. The N is the index of refraction of the film. The lambda is the wavelength of the light that we're interested in at the moment. M is just our, any integer we'd like that tells us that there's some periodicity here. And the 2 is a 2. Okay, so I know this is a lot of information, but I do have a practice problem for us on this topic. Oh, but I've just not stopped at all for you, huh? So, okay, I got talking and distracted. So let's take our 5-minute break, even though it's quite late, and give you some time to process this. I'll leave this slide up if you're wanting to stare into the depths of physics. Okay, so in the time that we've had, does anyone have any questions they'd like to ask or things they'd like to talk about for the thin films case? Yes. Yeah, so that's a great question. I'm really glad you asked. So in the text here, they say that that this top equation is destructive for the case where you only have one reflective phase shift. And so what that means is that in the destructive case, you see this red line, the red arrow does get a phase shift because we're going from a lower number 1 to a higher number 1.7. But that the green line, the one that goes through the thin film and comes back, doesn't have a phase shift. So it has a phase shift of 0. And that's because the material behind the thin film has an index of refraction that's lower. So 1.5 is less than 1.7. So we don't have a phase shift on that reflection. So it comes back to this image here, this one here, yes, where you can see case 1, as they call it, is where N1 is greater than N2. And so that's like a free boundary. And that's the case for this, for the green arrow. So the green arrow, N1 is greater than N2, 1.7 is greater than 1.5. So we have a free boundary, which means we have no phase shift. That's what's happening over here. Whereas for the red curve, N1 is less than N2. So you can see the red one, N1, which is 1, is less than N2, which is 1.7. So for the red one, we do get the wave coming back and it's flipped upside down, basically. So this is a phase shift of pi. And so, basically what I want you to be able to do here for these sorts of problems, I'll put the condition in the formula sheet, like the N1 versus N2. But I want you to be able to identify from the formula when we get a phase shift on reflection, and then say, okay, do I get a phase shift on both of the surfaces, the one on the front of the film and the one on the back? Or do I get a phase shift just on one of them? Or do I get a phase shift on neither? So all three are possible. And basically, if you get neither or both, then the top equation is constructive and the bottom is destructive. But if you only get a phase shift on one of the two surfaces, then it's flipped. The top equation is destructive and the bottom is constructive. And the reason that it's flipped, just to help your intuition maybe, is that when you have only one of them phase shifting, that's like saying that one of the waves coming out got flipped upside down. And so before we would have the two waves synced up, but if we had only one of the waves phase shift, now it's flipped upside down. So when we would have expected there to be constructive interference, now it's destructive because they're still matching up, but now just opposite one another. The phase shift is pi. So it's tricky. I'm really glad you asked because I do want to try to clarify as much as possible. I would encourage you to look through the section 8.2 of the book. It has a lot of, that's where I'm getting these diagrams and such. There's a lot of good material. And feel free to shoot me an email too if you want to talk more about it or come to office hours. But let's try a problem though and see if we can make something a little more practical out of these equations. So to keep unwanted light from reflecting from the surface of eyeglasses or other lenses, which also maximizes the light being transmitted. So the more we minimize the light being reflected, actually, the more light will come through the lens. This is an important principle. It's basically energy conservation, that however much light, whatever fraction is reflected, the remaining fraction is transmitted. A thin film of magnesium fluoride, which has an index 1.38, is coated onto a plastic lens with an index of 1.55. What is the thinnest film that will minimize reflection for a lambda of 550? Okay, so the first thing to do in these problems, like many physics problems, is to draw a picture. So we have air that we can put on the left, which has an N of 1. And then we have our thin film, which has an N of 1.38. And then behind that, we have our plastic glasses lens, which has an N of 1.55. Okay, so you can see in this case, when we go from the air and we're bounce off the film, we're going from a low N to a high N. So do we get a phase shift or do we not get a phase shift there? We do get a phase shift. So for this first one, yes, we get a phase shift of pi from that surface. Now for the second one, we're going from a low index again to a high index. So you can see in the example here, that green line didn't get a phase shift, but we were going from 1.7 to 1.5. Here we're going from 1.38 to 1.55. So again, we do get a phase shift. We're going from low to high. So low to high, yes, phase shift. High to low, no. Maybe that's the mnemonic, I don't know. Low and no rhyme, so high to low, no, maybe. Anyways, so here they're both yes. So we can use the formulas where the top one is constructive and the bottom one is destructive. We want to minimize reflection. So we want destructive interference. If we're going to minimize the reflection, we want the reflected light to cancel out, basically. And so we're going to use this bottom equation. We're going to use the 2t equals m plus 1/2 times lambda over n. And I guess I didn't say this before, but the reason we have a lambda over n in this equation is because the wavelength of the light in the film gets changed by a factor of n because the velocity is changing. So the wavelength is lambda over n. So anyways, we can, let me pull this up. We can, so they want us to find the thickness, so we can rearrange and solve for t. And specifically, they want us to find the minimum thickness. And so you can see m can be any integer from 1 onward for this formula and from 0 onward for this formula. So we just take m to be 0. So the fact they say the thinnest film, this means that m equals 0. So we can just write that t is 1/4 lambda over n. And now we just plug in our lambda, which is 550 times 10 to the minus 9 meters. Or we could also just leave this in terms of nanometers maybe, so that we get reasonable numbers. So there are no constants in these formulas, so the units you don't have to be as careful with. So 550 nanometers over 4 times, and then the index of refraction that we use in the formula is the one for the film itself. So 1.38. And this gives roughly 100 nanometers for the thickness. So we're like 550 divided by roughly 5-ish. And so this is a very thin film. You can see that it's actually thinner than the wavelength of light. And that tells us that we can use the wave model of light in this problem, right? This was appropriate because we're thinking about a context where the apparatus that the light is interacting with is on the same scale, the same size as its wavelength. If the film were very, very big, like the lens itself, then in that case, we would want to think about light as a ray. That would be the more appropriate approximation. Okay. And so one thing I want to point out here is that with this thin film, the way that we've analyzed it, it'll only cancel out the reflection for exactly 550 nanometer light, so greenish light. But in reality, the way that these work for even a simple case is that they kind of will cancel things out roughly around that wavelength as well. So by choosing the middle of the visible spectrum, you can kind of cancel out reflections in most of the light that is relevant to people. But for more complex situations, so for a lot of physics tools, instruments, they'll actually have like 100 thin films all layered on top of each other. in order to very precisely cancel tons of different wavelengths. So that analysis gets really tricky really fast because every time you pass a boundary, some light is transmitted and some is reflected. So you end up with, if you have 100 boundaries, you end up with hundreds of cases of interference. So be glad you're not having to do those problems, I guess. But this is basically where I'm going to leave it off for today. Oh, I wanted to give one more example, which is that this is actually part of the reason that we get eye shine in so many animals, is that the cells in the eye have different indices of refraction. And so there's a cool problem about this in the book, but you just have to look at that if you'd like to, where we have a thin film of crystals in the eye that leads to constructive interference in a lot of creatures, causing this kind of eye shine. So this is a bunch of alligators in a swamp. So we'll leave it here for today, but before you go, so since this is Thursday, I just want to say, on Monday, we don't have in-person lecture because it'll be Labor Day. Sometime today, I'm going to record a lecture video to watch, which I know kind of sucks, but it's a quick course and we've got to finish the material. So please do watch that. I'll try to release it today so that you'll be able to watch it either today or tomorrow or the weekend or Monday, sometime in that stretch. Hopefully you have a free hour and a half to watch it. And then I will also have extra office hours and a review session next week. I'm planning on posting a practice final soon. So the final will be 4 to 5 questions, one from each major topic. And like I said, we'll have a review session next week. So be on the lookout for more information on that. I have Zoom office hours tonight. If you're wanting to attend those, that'll be at 7. Posted a link in the announcements. And I think that was all the announcements. Oh, don't forget to finish up your project, right? It's due on Saturday. I've been getting lots of emails. I think I'm fully caught up right now. So if you have any problems, please do email me. I would rather you just talk to me about it. Okay, I'll see you all on Tuesday.